So it's a great pleasure to continue this series with Mark Banash. Mark was my very first graduate student at Princeton in 1982. And the world was very different in a large number of ways at that point. One that might be interesting to many of you is how different it was for foreign students. In particular, 1982 was the first year that it was possible for students from mainland China to come to the United States. And there was a very large program run by a variety of Chinese universities which sponsored students to come over here. I actually believe that Wei Tao Yang in our department was also one of the people in that very first class in 1982. But this first class of students had absolutely no understanding of what it would be like to be a graduate student in the United States. And so there were actually 4 students who joined my group, Mark Banish, Francisco Loaiza, and Frank Spano. Then a 4th one, who I won't name, who was a Chinese student, who joined my group for a month or so until he wrote back to his undergraduate advisor in China and was informed that the problem was that the 5-year plan emphasized things like catalysis, which another faculty member did, and only the Chinese 25-year plan included lasers, and therefore it was inappropriate for him to work for someone who was only in the 25-year plan rather than the 5-year plan, at which point he switched research groups. So it was a very, very interesting time. Mark was around with me for almost 10 years off and on in various things until he actually got his degree. And then, with a variety of things in between that he actually did. And he has had quite a range of industrial positions since that time. I think he'll talk a little bit about his history. And the focus is going to be, I think, on the most recent stuff he's been doing, which is looking at carbon nanotubes for real world applications. So Mark, the floor is yours.
Thank you. And before we get started, since I missed Warren's birthday last while I said hello, I just want to start this talk off with when I joined Warren's group back in 1982. One of the first things he said to me was, when you leave here, you will be a plumber, an electrician, a computer scientist. You'll understand electronic circuits. You'll know all of this stuff that's necessary beyond the theory and everything else that you know with respect to the science. And in the almost 30 years now since I've left the group, I have never once found my education from this man wanting in any way, shape, or form. As a matter of fact, I have found many others, unfortunately, wanting in theirs. So if the mark of a great teacher is what their students can take away and how often they can apply it, then I have nothing but good things to say about Dr. W. But let's get on. To start about this, rather than talk about my past, and I've worked for many different companies, I just want to give a little bit of a framework to some of the students and other people watching, because the future is more important than my past, I think, in terms of what I can convey to you. And with this slide, we're taking a look here at the top 10 chemical companies in the world back in the 1970s, according to C&E News. Some of them are familiar: DuPont, BASF, Bayer, all of these. And they were, once upon a time, these ruled the roost. And I worked for number 4, E&I, Mount Edison, for a while I was finishing up my PhD. I've worked for BASF, and the nice thing about BASF is if you work for them, they give you wine. And this is a bottle of BASF Rhine Riesling. But if you take a look now in 2020, you'll notice that many of these companies have gone away. They've disappeared. BASF is still there, but you'll also notice that there are now American and Europeans seem to have disappeared, and the gap has been filled by companies from Asia, which indicates the globalization of the chemical industry, and also more of an aspect now on consolidation rather than growth. And what this means is that the types of research organizations that you could work for, and when I was at Princeton, American Cyanamid, International Flavors and Fragrances, Mobil, Union Camp, all of these companies had R&D centers in the Princeton area. They are now all gone. So you've had a major downturn in R&D. I worked at Roman Haas for a while. This is gone. It's been replaced by this. The facility is still there, but it is now no longer a research lab. It is an innovation center for small, high-tech businesses in Pennsylvania to use the facilities and to try to grow businesses of their own. This is my lab in Baltimore, or when I worked for SCM Chemicals and Millennium Chemicals. You notice there's no laboratory. What that is a fly ash pit. The building was leveled and turned into a dump for waste from the local coal burning power plant. Sometimes what happens is rather ignominious. I worked for Anychem America in Monmouth Junction, New Jersey for 5 years. It's no longer there. The building's still there, and you'll see that it is now a skating rink. So there have been some changes with the types of availabilities and opportunities in terms of them being pure corporate things. Corporate research has sort of diminished. And sometimes the buildings are still there, but they just get repurposed. So my headquarters is right here. This is my house here in Bedford, New Hampshire. That's my current office, and I'll probably stay here for a while. But the private sector right now in R&D is that it's been replaced by smaller companies, many small companies and startups. This is great. A few weeks ago, Dr. Lin gave a talk, and he was talking about why you should move to Boston or moving to Boston. If you want to move to Boston and you want to be a chemist or a physical scientist, this is a great area. You call me up, I could put you in touch with 5 or 6 small companies, all of whom are doing chemical related research. And all of these opportunities, as I said, come from your network, friends, colleagues, alumni. And this is why all of the people that you meet throughout your career are going to be very, very important to you. Funding comes from the same sources. A perfect example of this was a few years ago, I attended something at UMass where I talked to a guy who was running a firm, who was an investment firm for the Rockefeller family. It wasn't the big Rockefellers. These were the Rockefellers that only had $10 or $20 million apiece. And I talked to him about how they funded startups. And I said, do you look at a business plan? Do you look at the technology? He goes, no, basically we go in, we talk to the people. If we like them, we give them the money. So, excuse me, that's my dog. So she's just excited because the FedEx truck's outside. So your resources do as well. The other thing that's very important is any of our old Princeton alum who are on the line today, TigerNet, and I'm sure Duke has an equivalent, is wonderful. I needed a lawyer one time Sunday afternoon in the middle of the summer in Texas, went on TigerNet, had an excellent lawyer the next morning. By 5 o'clock the next afternoon, the matter was settled in my favor. So your network, I cannot stress how much that's going to be. Also, expect a 3 to 5 year timeline that you're going to be involved with something like this for 3 to 5 years. The opportunity will either develop or it will be reach a natural logical end. But that's typically how some of these things work out. And as I mentioned at the top of the talk, drawing on every part of your education and training, when it's 11:30 at night and you're in a pilot plant in Rapid City, South Dakota, and the hot water heater on the epoxy mixer dies, you better be able to figure out how to fix that. And so your graduate's training is excellent for this, being able to not panic and fix things. There is one thing that's really good about all this. You may never have to write a grant proposal again in your life. I let other people worry about getting me money. I mean, I get my own money, but in terms of a lot of the proposals, I corroborate with people, but most of the time I cannot think of the last time I really seriously wrote a grant proposal to fund my work. So I go into the lab and have fun. Having said that, let's get to the meat of the talk today, which is to talk about carbon nanotubes. And I'm going to talk about 3 challenges that exist out here now with nanotubes. There are taxonomy. There's 3 common forms. We talked about this briefly before the talk. Single wall nanotubes, which are just that. They're rolled up chicken wire made out of sp2 hybridized carbon. They generally come in 2 forms, metallic and semiconducting. And that property is determined really by, if you want, for want of a better term, the degree of twist around the bond axis. There are indices associated with this. Certain combinations of indices yield metallic conduction versus non-metallic or semiconducting. They generally have diameters between 7/10 of a nanometer and about 2 nanometers. Dual walls are just that. They have 2 walls. Most industrial production is not centered on dual walls. They do occur, but they occur as a side product. Most production is multi-wall nanotubes. These are the easiest to make. They typically have diameters greater than 2 nanometers. And between the walls, you've got a standard graphite spacing of about 0.34 nanometers. So it's really easy to count these things and figure out how many walls that you have. Why do you want to use CNTs? And the answer is they have a very high thermal conductivity. They have a high electrical conductivity if you're working with single wall tubes. They can be approaching metals. They can easily be the equivalent of silver and possibly even come in range of copper. And so you've got a material which can stretch, it doesn't fatigue, it can bend again and again and again. It has a very high tensile strength. The most interesting thing to me, though, actually is the low thermal expansion coefficient. One of the strangest things with nanotubes is that you can take them, you can throw them in liquid nitrogen, you can crumble them up, and they just remain flexible. It's really quite interesting to play around with this kind of stuff. But if we look back about 15 years ago, there were many major CNT makers. Single walls, CNI, Dr. Smalley, his Nobel Prize work in nanomaterials, started CNI down in Texas. A wonderful company called SWINT, Southwest Nanotechnology, made single wall tubes out of the University of Oklahoma. Thomas Swan in Consett, UK, up by Hadrian's Wall. Real nice company, very professional, understood statistical process control and other things. And over in Europe, there were many major multi-wall manufacturers. Arkema, Bayer, they got into a friendly rivalry there for a while. Nanosil in Belgium. You're talking about facilities that can make literally tens of tons, if not hundreds of metric tons a year of nanotubes. And so the future was bright. This is from CNE News from 2004. You can see what they forecast was going to happen with the market. Everyone and his brother and sister was going to want nanotubes. And what you see on the right is an Arkema nanotube reactor capable of making about 30 metric tons. When it made 30 metric tons, Bayer decided that they had to up them, so they went to 60. Arkema decided they needed to improve it, so they went to 80. Bayer wasn't standing still for that, so they went to 200, and Arkema went to 400 metric tons, eventually being able to produce that many multi-wall nanotubes. There was only one problem. Here, you'll notice many of these companies are gone. Thomas Swan is still there, no longer makes it. CNI was bought by a company called Unidyne about a decade ago. Southwest Nanotech is still there. They make nanotubes on contract. Arkema and Bayer, that foolish competition, in the end, there was no market for it. And I know a gentleman who got the entire Bayer nanotube stockpile and carted it away from outside of Ludwigshafen in 8 tractor trailers. I don't know where it is right now, but it's somewhere in Germany. Nanostil is still in business, and they make small amounts of material. And Oxiol is a Russian company, and they've just come online with making a lot of nanomaterial. They're located, I believe, just north of Georgia in the former Soviet Union. So what happened? Why did this crash? Well, there were no scalable processes, really, and I'll get to that in a moment. There were no analytical methods for determining quality. Getting single wall nanotubes, isolating the metallic conductivity ones, proved to be harder than they thought. There was poor adhesion in composites. If you want to take a nanotube and take advantage of it, you want to make a composite out of it for something like aerospace, that's great. You can mix it, but you'll find that they often will clump up. They'll turn the melt rheology or the just plain viscosity of a resin into concrete. There's a lot of issues with mixing them in. And plus they were short. A lot of these tubes were under 5 microns in length, which were much too small for applications in mechanical strength and things like that. Also, there were few applications that could sustain the price point. I had one guy told me that, yeah, I can sell these things for $500 a gram. And I told him, no, you can't really. No one will pay that. And I was right. I'm not happy about that, but it never turned into a real market. And there was a build it and they will come. So there was this idea that they had to build things and build the infrastructure before all the applications became apparent. So the lack of applications, the inability to make this stuff at scale at a low cost by many of these companies, not everybody, but most, and the fact that there were no quality tests or ways of checking the material to see that it would actually perform as functioned, all of them sort of short-circuited everything. I'll give you an example of one of these processes. This is the CNI single wall process. It was called the high pressure carbon monoxide process, or HIPCO. It took advantage of something called the Boudillard reaction. It basically used high pressure carbon monoxide and a metal nanoparticle as a catalyst. The idea would be the material would collect on the metal particle, organize, and this required high temperatures greater than 700 degrees and high pressures. Now, as chemists know, we have 3 tricks up our sleeves: concentration, temperature, and pressure. And when you require any 2 of those, they generally cost money. So this was a very expensive process to run. Also, thermodynamically, this is not a particularly good process. This has been studied for almost 100 years. The equilibrium constant for this are known. You'll see that at high temperatures where you typically have to run it, the equilibria favors the carbon monoxide and not the conversion. So thermodynamically, this was not a good reaction to scale. And so they were never really able to get the cost down on this. And the result of that was that the single wall tubes they made may have been perfectly good in terms of quality, but economically, this was a bad reaction to scale. There have been a few real world applications with this material, and here are a few of them. On the left, you'll see the Stealth bat made by Easton Sports, and the bicycle handlebar, the Monkey Light handlebar, and the Stealth hockey stick made by Easton. These were products that I helped design and helped formulate the epoxy resins for. The interesting thing about the top one was that the little ring that exists between the barrel and the grip on the bat, there's a little ring there made out of epoxy with nanotubes in it that stops the bat from stinging your hands. The handlebars had reduced flex, which the riders liked. And I'm not quite sure what happened with the hockey stick, but I know they made it. And on the right-hand side, you see the Juno probe. On that, there are some carbon nanotubes that came out of a process I was working on at Nanocomp, not really high tech or excuse me, not really at low cost, but very lightweight, ended up going on the Juno probe. It's a form of EM shielding for the thrusters. So I may never get the Nobel Prize, but at least one of my baseball bats is in the Smithsonian, and something I made is 100 million miles from Earth. So I'll live with that. So what do they do now? How do you make nanotubes at scale now? And the answer turns out to be something called a horizontal tube reactor, which is exactly what it sounds like, something about 6 to 9 inches in diameter, 2 to 3 meters long, chock full of hydrogen and ambient pressure. Temperature is about 700 to 1300 degrees C. I'll explain why that is. You need a carbon source gas. Right now, methane is preferred. Any simple hydrocarbon will work. I know I've made nanotubes out of everything. I have made it out of diesel fuel. I have made it out of pesticide. Any carbon source material will make nanotubes of varying quality. There's a catalyst precursor. So typically the catalyst itself is not created ex situ. It is fed in as a organometallic compound. Ferrocene and iron metacarbonyl are nice because the iron is already in a zero valent state and will therefore condense from an aerosol into particles that can grow the tubes. Sulfur is often used as an adjuvant. The role of sulfur, to me, still has not been completely elucidated. It is commonly used, but what it's doing in the process. So here's an output of what a tube reactor actually looks like. If you take a look down the business end, and if I started going here, you can actually see this black sock, as we call it, that are filled with multi-wall nanotubes. coming out. The reason it's rotating is that it's collecting on a drum. So a long hollow sock of interlaced nanotubes will emerge from the reactor. It will be collected on the drum. And the reason for that is that this will make a phyllodoe-like structure that will form a sheet. And you can see that sheet in the upper left-hand corner, one of what these sheets look like. On the right, you can see that you can also process this into things like slurries and liquids with a solvent. And thus you can mix it with things like paints, if you want to do that. And at the bottom, you can see you can also draw that sock down into a yarn or a fiber. And that is a prototype hydrogen storage tank for NASA. So this is what you can do with material that comes out of these reactors. But to get to the interesting science of it, if you take a look close up at these things, you will see that there are these networks of tubes. And in fact, they are nanoscaled. One of the most fortunate things I ever had in my life when I worked at Nanocomp for 5 years is I had an SEM all to myself. I love that. I had a trained SEM microscopist all to myself. And for years, Paul Anzalone, great guy, did all of these things for me. And you can actually see the network of tubes, and you can see the measurement of the tubes. Those little hard balls of things, I'll explain what they are shortly. But one of the problems with making nanotubes is that small changes in reaction conditions and fuel formulations can create huge morphological changes. I refer to this as the pasta model. What you saw before was capellini. On the left, you see ramen, and on the right, you see linguine. Small changes in reactor conditions in terms of altering fuel ratios, changing methane to ferrocene concentrations, altering pressures slightly, will create these variants. Why? I don't know. Needs to be studied. So, talking about study, how do we know what to do? What level of science might be appropriate to take a look at this, at least from a first level of approximation? And for that, I went back and used classical thermodynamics. And the reason was there's a very interesting Russian gentleman named Parman who studied this and gave me a sort of rule of thumb, which you can read there. Anything that's sort of 100 atoms or more, you're okay probably using classical thermodynamics, not worrying about these things as clusters or other things. So this was just the first level of doing a check and saying, okay, if I'm going to study these things, let's just use first level classical thermodynamics as sort of our equation grab bag to understand things. And this is why. If you take a look at a standard proposed growth scheme for nanotubes, you start off with a metal nanoparticle in a liquid state exposed to a feedstock molecule. What happens is that that feedstock molecule will land on the surface. It will form a surface layer. Decomposition products will move off, and then the carbon will rearrange itself and form a nanotube. So that's the proposed growth process. And you can see that this has been proposed a long time ago. It's 15 years old. And this is the steps that were proposed for how this worked. And it was also observed in TEMs. I had a chance to work with Sir Harry Kroto for a small time. Harry was a great guy. He cared about three things: physics, his wife, and his garden, often not in that order. But Harry talked to me about this, and he confirmed, yes, when you see these things growing in an SEM, this is the growth process they saw. Somewhere around here, I have a little drawing that he did over dinner at a restaurant down in Boston, but this conveys Harry's meaning without having to show the drawing. So the question is, where do these nanoparticles of metal come from? And the answer is, like I said, you typically will shoot ferrocene or iron pentacarbonyl in. They will decompose, liberate free iron atoms, and then you expect these nanoparticles to form. Well, why and how? And if we go back to classical thermo, if we look at the Kelvin equation for condensation of droplets, very simple, straightforward equation, wonderful. The vapor pressure of iron is well known. And even as a liquid, it has a vapor pressure. It's very, very small. And so it's easy to calculate how big these droplets are going to be. Are they actually going to be nano-sized? Are they actually going to be, is the thermodynamics favoring them at these temperatures? How many of them are going to be in these drops and things like that? all of the types of things that you can answer from just some very simple free energy equations. And you start finding out that there's a sort of a critical radius, a critical number of atoms, where under reaction conditions, these things are thermodynamically stable, that they're not metastable and they're not going to fall apart. And it turns out for iron, and iron is used because, first of all, it's cheap. Second, it's not toxic. It's better than using cobalt or nickel, or in some cases, ruthenium, which I won't get into. You can generate droplets, things that are about half a nanometer or so in diameter of iron are stable at these temperatures and pressures. And that's important because you'll see here, we start talking a look about diameters of particles, that when we start getting to about 100 atoms, which is sort of the cutoff, we're at a diameter of about 1.5 nanometers. And why that number is important is because there's a relationship between the nanotube and the nanoparticle that grows it. And that is that the diameter of the nanotube, that ratio to the diameter of the particle, is 1.618. And that's a very interesting number. If anyone knows what that is, you can tell me what it is at the end of the talk. But it is a number that occurs very frequently in nature. And so if you have a particle that's about 1.5 in diameter, 1.6, you're going to start making nanotubes that are about a nanometer in diameter, which are small enough to make single walls. So you can still use classical thermo to describe the processes that are going on with these little drops. Now, here's something that's really interesting also as you drop down to these nanoscales, the melting point changes. This isn't me, this is Gibbs and Thomson 150 years ago studying this with the Gibbs-Thomson equation. And if you look at it, it looks extremely straightforward. Enthalpies of fusion, densities, sizes, surface tension, surface energies, all of them are in there. It's just arranged quite nicely. And you can see the size relationship between the particle diameter and the melting point. So at the reaction conditions where you typically are for these things, you'll see that most of the particles that are in that range will remain liquid. And so you'll grow nanotubes easily because those particles will remain liquid. Now, as particles coalesce, they will remain liquid for a small amount of time as they heat. Heat is the way that they lose energy in order to condense down. So they will remain liquid for a little bit longer, but very nice. Now, one missing piece to this puzzle, and I really have to say this, is due to this gentleman named Seifert's. This is not the radiation Seifert's, this is someone else. Adolf Seifert's studied metal gas interactions about 100 years ago. And the reason why I have that article page up there is because I actually have this journal over there in my bookcase. And the reason why I have it is because it was one of these articles that was constantly referenced in everything, but I never could find anyone who actually showed they read it. They just sort of referenced it. So I went out and actually got this, and I can read German fairly reasonably, so I read it, and there were some things that were worth noting that kind of got lost in the translations over the 100 years or so. And what he found out, and this is very interesting, and it'll become obvious when I say it, that molecules, simple polyatomic, simple diatomic gases, when they encounter a liquid metal, dissolve as atoms. They don't dissolve as intact species. And so things like hydrogen easily exist in equilibrium with the dissolved species inside them. Of course, carbon is the odd beast because of all the things in organic chemicals and your standard hydrocarbon. Carbon's the only species that doesn't form a diatomic gas. It has to stay stuck. Hydrogen, oxygen, nitrogen, all the rest of them can go back into the gas phase or at least exist in equilibrium. But carbon, once it hits a liquid metal drop, is trapped. And so the revised growth process is that the catalyst, again, must be in a state. The melting point is dependent on the element and particle diameter. I mentioned ruthenium. I once did an experiment with ruthenium as the material. And we grew nanotubes, but because ruthenium has a different melting point, different other terms, surface energies and things like that, it shifted the diameters of the tubes that were made. So you have to choose wisely depending on what you want to make. But the carbon source does not undergo any type of catalyst process. In fact, it just breaks apart. It dissolves, for want of a better term. And surface energy means that the carbon is going to stay near the surface. It's going to lower surface tension by remaining not inside of the particle. It's going to remain on the surface, which is great because it's going to move around a lot. So the carbon will self-assemble into a cap that extrudes into a tube. So it's technically not catalysis. It's more like a solute crashing out of solution. And that's important because people have called it catalysis. I don't think it is. Now here's something else that's interesting, and we can take a look at this. This is a species I made, and you can see these little balls. I said we would come back to them. What we're seeing here is we're seeing nanotubes, and you're seeing those little balls of metal around there. Now, you do an elemental analysis, you find that about 90%, a little 90% is carbon. About 10% of this is iron, and there's some trace sulfur with molar ratios, and you can see that there's probably about 40 times by molar ratio iron to, or carbon to iron in these things. There's so much iron in this stuff that it ends up aggregating and forming large non-reactive blobs of the stuff. And so it's not catalytically or chemically active. And as a matter of fact, this is why a few years ago, when Warren was kind enough to say that he could run some carbon-13 NMR on me, and I told him there's iron in it, well, you can see where that's going. So the first challenge, the first goalpost here is CNT requires a liquid metal droplet to generate the free carbon and to provide the organizing template for the CNT dimensions. But if you do an analysis on that drop, you'll find out that very little carbon or very little metal is actually needed. A nanotube, multi-wall nanotube, has a billion carbon atoms if it's a millimeter long, and these are. It only needs 3,000 or so iron atoms in a droplet to make a tube that size. So you've got a lot of parasitic dead mass in this stuff. And so using the aerosol precursor method produces dead mass. It produces particle sizes that are difficult to control. So the first challenge is, how do you generate a metal particle of the right size, the right composition, so that it doesn't aggregate and form dead mass, which is chemically inert? Here's something else. I just mentioned this about a second ago about the tubes and their lengths and how many tubes you're dealing with them. Here's something else. You saw how quick that stuff was pouring out of the tube, how fast it was. Typically, if you measure some times, you'll find that a nanotube that long forms in about a second or two. But if you go back to your Castellan and you dig out your equations on kinetic theory and calculate the collisional rates between the reactants and the metal nanoparticles at these pressures, you'll find that the collisional rates are on the order of 10 to the 6th a second, or about probably 100 to 1,000 times too slow. Now, this is where my math teacher in high school, Mr. Walls, would draw two crossed swords indicating a conflict. So the question was, okay, why are these things growing as quickly as they can if they aren't encountering reactants quickly enough? So we get to this. This is the theory of mine, which I'll get into. These are polyaromatic hydrocarbons. Phenanthrene, anthracene, pyrene, all of these. They're very common. They're found in outer space. They're found in molecular clouds. Matter of fact, when they were first looking for buckyballs, they found them out. Proto found them out in some cloud somewhere. These form inside a reactor anytime you have the decomposition of a carbon source. And the question is, how do I know this? How do I know that these materials are present? And the answer is because I've stripped them off myself. On the left, you see what's called a Soxhlet extractor. Many physical chemists don't run these, but it's just a little extraction tool using chloroform in this case. Or on the right-hand side, you see a supercritical fluid wash. This is just a fun, talk about fun. If you've never played with supercritical fluids, look them up. They're a lot of fun. A colleague of mine named Hans Schoeman has a company down in Andover, Mass. That does supercritical washing, and he and his team were able to extract various things off the surface. A few weeks ago, Dr. Spano talked about his work with polyaromatic dimers and trimers and larger aggregates. And this is why I was interested in them, because one way of confirming their presence is with ultraviolet spectroscopy. Another is by GCMS, which I fortunately had access to. What's even more fortunate is that I had access to the NIST library for looking at these things. And so identification now is a lot easier. You can just ask the software to identify these peaks for you. Check it, but it will do it for you. Now, why are polyaromatics and nothing else particularly interesting? And we'll go over to HOMOs and LUMOs. This is pyrene, a very stable and frequently occurring polyaromatic. Sometimes I found this making up 5% of the mass of the carbon product that comes out of a reactor. The HOMOs and LUMOs, which everyone has seen. The interesting thing to me is I did these calculations myself and I did them on my phone. There's a web app, or there's a thing called WebMO, which is a phone app for Android, which allows you to calculate HOMOs and LUMOs of aromatic hydrocarbons. The future is certainly here. And this is why these are important. The HOMO-LUMO gap is basically a ruler for how stable these things are and how they will react and what they will react with. This has been long known. Here's a paper, which is a really nice paper to read. And you will see that as PAHs undergo clustering in the gas phase, you're going to get changes in this HOMO-LUMO gap. And as they adsorb on surfaces, they begin to undergo chemical reactions. So they'll form in the gas, and then they will start aggregating and reacting and forming larger sp2 carbon hexagonal structures. So this gets to the second challenge. Right now, what I see in the reactors I work with, the growth is too fast to be explained by simple kinetics. Other carbon species are forming. Methane is well known to pyrolyze into ethylene, benzene, other things, and to polyaromatics. As the CNT grows, its cross-section is increasing over time. It's getting bigger. So if the cross-section is getting bigger, maybe that's explaining why I'm seeing an increasing growth. The pHs are there. Their HOMO-LUMO energy shifts are proven experimentally and theoretically. Do the PAHs explain the higher growth? I don't know. But if they do, it would mean a drastic change in what is used to make nanotubes. Coal tar and other bad chemicals could be used to make them. And now we'll get on to the third challenge, which is characterization. How do we know what we have? Well, there are three tools in the nanotube person's toolbox: spectroscopic, imaging, and thermographic. Raman spectroscopy is the one that tells you mostly structural, what type of tubes you have. Are they multi-wall? Are they single-wall? Are they metallic? How big are the metallic tubes? How big are the semiconducting tubes? Raman is the tool for that. Imaging gives you an idea about the network, gives you about an idea about how big the tubes are when they're multi-walls, and other things like that. But, and thermogravimetric is very handy. Why? Because it's extremely easy to run. This is basically an analytical balance inside of an oven. And you heat the oven and you watch the mass loss. And so it's extremely easy to run. You get nice curves like you see there. There's the mass loss curve in green and the derivative or rate change. So when we look at that, and I'll talk about why this is important in a second, the first two techniques are primarily resolved to structure, but not to chemical processes or chemical properties. I don't know from looking at a Raman, or necessarily looking at an SCM, how this is going to interact with a solvent, or how it's going to interact with a resin, or how it's going to interact if I want to functionalize it or tack something on it. And so kinetics, TGA, simple, very simple experiment comes into play. This is a tube called a 7-6 tube. The 7-6 tube is a non-conductive, or it's a non-conductive, a semi-conducting tube. And this is sold by Sigma Aldrich as a very pure nanotube. And this is the derivative of the mass loss curve done at 2 degrees a minute in a TGA in an air atmosphere. And what you see on the bottom there is a kinetics curve. That is something called the Fraser-Suzuki equation for the type of kinetics that occur at these temperatures for the combustion of materials. And if you go back to your graduate thesis and you pull out your line fitting routines and you download a free Fortran compiler, you can fit these curves. And you find out that statistically, this is not a single substance. There are actually two substances in here, statistically by analysis. So what someone told me was a pure material. Turns out that chemically, it's probably not. Well, prove it. You know, you can get two curves. Well, there's something called Kissinger analysis. And what Kissinger analysis allows you to do is to take the peak of the activation, or the peak of the derivative curve, and to plot it against the heating rate. And when I did that for the peak in blue and the peak in red here, you'll notice that I got two very straight lines. Now, this isn't confirmation, but it's certainly not dismissive. There might be something here. They might literally be two different chemical species in the material. I can tell how much of them there are, and I can tell something about their properties by at least how they operate, how they interact with air. I can find that they have different activation energies, and if I plug these into a simple kinetic equation, I can get the prefactor. So I can see a little bit about each one of these being slightly different from the other, even though the ad on the box said that this is a homogeneous material. It isn't, at least in terms of composition. What else can we learn from TGA? Well, like I say, hints from another allotrope. Studying coal has been a long use of TGA and a long use of studying things. And they've developed something called the distributed activation energy model, which says that if I have a surface like graphite or coal or any of these other carbon materials, the surface doesn't actually have a single activation energy, but actually has a distribution of them. And if you use the equations for that and you take that same data that I showed you for the 7.6, you get an idea of how different these activation energy distributions look for each one of the components. One is very narrow, reasonably narrow. The other is kind of broad. Now, to me, that tells me, at least suggests to me that, well, in terms of chemical heterogeneity, blue is probably far more heterogeneous than red. I don't have any proof of it, but at least I have something that suggests it, and I have a test that I can run, and I can quantify it, and I can analyze it. And even better than that, I can have this analyzed and by my peers. And so I have asked some people, I'll credit them at the end of the talk with having checked this over. I mentioned at the beginning, the Russian company Tubal, this is their product. When you actually plot the distribution as a standard distribution, you get something called a Weibull distribution. I'm not sure why. I don't understand this yet. But I do know that people are claiming that you put this Tubal material in epoxies, in other thermal plastic materials, or other thermal resins, I'm sorry, and you get very good results. Well, I can tell you that the surface has this very interesting distribution to it. And I have to take a look right now about whether this has anything to do with anything. So that we get to our third challenge. Raman and electron microscopy can confirm the presence of nanostructures, but nothing about the number of tube types, the relative amounts, or the chemical properties. TGA can get us the number of distinct components, their relative concentrations and amounts, but currently only their chemical properties with respect to combustion. There's been no correlation as yet, I'm working on that, with manufacturing conditions, final properties, or performance and applications. And so what other techniques are there? I don't know. Oops, sorry. Get up here, sorry, jump to the top there. So, pay no attention to that. While the physics of the metal nanoparticles that seed the nanotube growth are reasonably understood, methods to control them during synthesis are wanting. Initial proposed mechanisms do not match the observed reaction rate, and other mechanisms require more proof. And we need other things that can confirm the nanostructures, specifically about chemical properties. So I'll leave you with two final thoughts. First is this. I keep this up over my office door here because I have run into people in nanoscience who swear blind that what they're going to tell me is the truth. And one thing I did learn from Warren was never, ever to accept jargon. Okay, so Dr. Mossbauer's quote here is correct. Learn to explain it. I don't have a cat, I have a dog. And I'm pretty sure she's sick of me listening to me by now. But the other thing I'll leave you with is this quote from the science fiction writer Leslie Stevens. And don't worry about whether you're in a big lab or a small lab or at a prestigious place. Worry about the quality of your work, because that breakthrough will come when you care and you apply your time, you apply yourself, and you apply your thoughts. And if I leave you with one thing, write everything down. So my thanks to Dr. Angela Height-Walker, Elizabeth Mansfield, and Jeff Fagan of NIST, with whom I've collaborated on the TGA and the Raman work. Dr. Rachel Stevenson of Huntsman, who's my excitement anchor. Whenever I come up with a crazy idea, I say to Rachel, what am I doing? Is this right? And she says, no. Dr. Glenn Irwin of Rice, with whom I'm collaborating now on some things, and Mr. Peter Antoinette of Nanocomp, who whenever I went into his office and asked for some crazy material, always signed the purchase order. Extra credit very quickly. Here's something that bothered me. Nanotubes conduct on their own, measure a single tube, it conducts. Put them in a bundle, the dispersion forces create a perturbation. Does the perturbation destroy the wave functions so that the wave functions of the nanotubes in bundles are no longer metallically conductive? I don't know. But I guarantee you there's a paper or two in that. So here's our obligatory embarrassing photos, Warren. Sure you recognize some people. On the upper left-hand corner is Francisco Loaiza Lemos. This is your first group. There's me. I'm staring in the middle there at a laser. And Warren's not in the photo, but he must have just left the room because the laser is working. And I'm standing there trying to figure out how he got it to work. Frank Spano, Dr. Spano is professor at Temple. He gave a wonderful talk a few weeks ago. One of the most intrinsically smart physicists I've ever met is Frank. In the lower left-hand corner, Dr. Jenny Bates, out in California, where I believe she's in the administration of a college. Dr. Mark McCoy there, standing in front of Warren's first experimental NMR at Princeton. And Dr. Mark Hayner, who I understand will be coming up very shortly and giving a talk of his own. This is Dr. Saketu Gandhi, who I do want to acknowledge. If it wasn't for Saketu, I never would have fixed any of the problems I have with my vacuum line. He knew so many things about it. I am very thankful to Dr. Gandhi for his mentoring and his knowledge about those things. And of course, we wouldn't be anywhere without a picture of Warren. You can cringe now. By the way, that's from the Princeton graduate student yearbook. He wouldn't let us take his picture, so we had to use the one from when he applied to school. And I know that because that's your first office in New Frick, not your second office in New Frick. And in between there, you had the office in Old Frick, and that's where the picture of Francisco was taken. So, and to give everyone a little perspective, you never know who runs this universe, but on the day of my final public oral, this was the Calvin and Hobbes that ran.
All right. Mark.
Okay. Thank you.
Thank you for a very, very entertaining talk. So yes, and in fact, Mark McCoy will also be speaking in about a month. I've got him on the schedule as well.
Excellent, excellent.
I've been trying to draft Francisco, and I haven't yet succeeded in that. And Jenny has said no because, yeah, she's an administrator at Santa Monica College, but she says that she's actually on some of these presentations. So, all right, so as usual, please raise your hand if you have a specific question. And so let me start with Boyd.
Yes, that was very interesting. The number is the golden ratio, but I guess the question is, why did it pop up?
That's a very good question, and got it in one, Boyd. Excellent. That's an extremely, the only thing I can ever think of, and this is probably specious, is Penrose tiling. It's one of the few things that I know where you get aperiodic tiling. And the
so you think it's a quasi-crystal?
Huh? No,
you
no,
think
it has
it's like quasi-crystal on the surface? Like, why would Penrose tiling come up?
Because of the bonding between the nanotubes or the carbon naturally forming pentagons and hexagons.
Okay.
I mean, I don't think you get this with boron and nitrogen when you try to make boron nitron tubes. I haven't looked at them. That's the only explanation all the time that I've ever been able to come up with is Penrose tiling. It's aperiodic, and that the ratio between the size of the surface on which it's growing and whatever's coming off seems to be the golden ratio.
And that's how you get the number 5 in there. I see.
That's it. I think, okay, I could be wrong. Nobody's ever corrected me because I don't think anyone's ever thought about it. But like I said, I wish I did have a graduate group. I have a lot of projects I'm sure I could give them. But congratulations on the golden ratio.
Thank you.
So why does a carbon nanotube ring on a bat cut down the vibrations significantly?
The epoxy itself actually shatters. The energy can be transferred more efficiently throughout the epoxy. There's a wonderful YouTube video, if you ever see this. It takes different shapes. It takes a square grid and a hexagonal grid, and it pushes down on the end of the grid, and you see how the energy is spread. What they were having problems with was that the epoxy was, the energy was going into shattering the ring. And so people were paying $400 or $500 for one of these baseball bats, and they use it, and the ring would crack after about 200 hits. By putting the nanotubes in there, we were able to basically distribute the kinetic energy more effectively throughout it. I don't know if it converted any of it to heat, I don't know, but the bat went from having roughly 200 to 300 hits to about 700 or 800 before it cracked. And that's how that came about.
Okay. So obviously the carbon nanotube market didn't explode the way that C&E News thought it would. How much? So what is the market actually today?
That's a very good question. And my answer is it has two things. First, it has to do with this. And I don't know if you can see this glowing.
Yeah.
Those are carbon dots, carbon nanodots. And I made them myself in my oven in a little pressure device. I think that carbon nanotubes integrated with carbon nanodots have a wonderful application as electrodes in fuel cell and flow battery applications. The reason for that is that the existing technology is graphite, and that graphite does not have a high enough electrochemically active surface area. It also just doesn't have a high surface area. Most graphite electrodes have surface areas of 10 to 15 meters per squared per gram. A carbon nanotube is 10 times that. Also, functionalizing those surfaces are very difficult, but functionalizing these things is not. They integrate extremely well. And so I think that things like electrodes are a huge market for this. They've just not been developed. Plus, that's another reason to get the metal the heck out. Because if I were to go to a flow battery company and I said, guess what, this thing only has 20% by mass iron, I'd be shown the door quickly. So that's where I think the applications are. I think that they are in electrochemical applications like cars, vehicles, trucks, anything like that. That's where I think the application is.
Okay. Jay.
I'd just like to answer your question, basically. I think right now the biggest carbon nanotube market is in battery. Unfortunately, all the big companies making these nanotubes are in China. They are making a couple of thousand tons per year. Just to add into a battery to make the life of the lithium-ion battery longer. So I know a couple of friends there who just Fei Wei and others. They are making they basically cannot make enough. The people are waiting in line to get their nanotube for their battery work. That turns out to be surprisingly the biggest market for carbon nanotube for now.
Yeah. We may have found the killer app, or at least an assassin app. You know.
Right. I think Fei Wei was recently said something like, basically his company was saved by battery company. He never expected this would be the biggest market for carbon nanotube. None of us expected, in the early years, but turns out that's where people make most of money from carbon nanotube.
I believe it. Epoxy composites and things like that. There was some work in heaters for a while, making things like resistive heaters for automobile seats, and Ford was in this, making heated steering wheels and things like that. But as a friend of mine is an MIT grad, he always has the Mylar rule, which says, if I can do this with a cheaper, faster available material like Mylar, why am I going to buy this? And so that's what ultimately did in those applications. There just wasn't enough of a differentiation with nanotubes for those applications, especially price point. But no, I think electrochemically, it's a really interesting application.
Other questions from anybody? Okay, thank you. Well, Mark, you mentioned that you may not have a Nobel Prize, but you have something in the Smithsonian. Our next speaker may not have anything in the Smithsonian, but she does have a Nobel Prize. And that is Donna Strickland, who worked for me at Duke for 4 years. She did essentially the job that Martin Fisher does now. She ran the laser facility that Princeton had, which was also partly supported by the state of New Jersey. From there, she went on to her faculty position at Waterloo, where she's been ever since. Obviously, she's been giving a lot of talks over the course of the last year and a half, but she was very pleased to give a talk where this isn't going to be her Nobel Prize lecture. This is going to be talking about the research that she has been doing over the years, and it should be a lot of fun. So same time, same place. You'll see the advertisement shortly.
Great.
Yeah.
And just one last thing. If anyone has any questions about working in industry or any other things, there's my email address on the slide there at the bottom. Please feel free to contact me. Like I said, the power of the network is really what's going to be your best friend in doing any type of things professionally. And even if you just have a question, please feel free to contact me.
Okay, and again, thank you. And that's also very helpful for a lot of the students, again, who need to see sort of the ranges of things that you can do, having started off doing shaped laser pulses.
I found a printout last night from the old Mink 23 system in the basement of all things.
Yeah, okay.
Yes.
I doubt I have any of those anymore, but all right. Thank you very much, and we'll see you folks next week.
Okay, thank you.
Thanks. Bye.
And again, you have no problem with my having this recorded, Mark?
Oh, of course not. Go right ahead.
Okay, sounds good. Bye.
Thank you. Bye-bye.